quantum mechanics. The theory of quantum mechanics, or maybe, rather the discovery of the quantum fields, plays one of the major part in the modern-day physics. Quantum mechanics, in general, is the key to the description of behavior of matter, in the world of very small, the quantum world.
Can have a sing-along.
Quantum, or quanta, is the Latin word for amount, meaning the smallest possible unit of any physical property, or quantity, such as energy, time, or length. According to quantum mechanics, everything is quantized. Literally, everything. And one of the things we've discovered from the fact is that light, which we think, or are supposed to think as a wave, due to a number of phenomenons like diffraction, refraction, reflection and polarization, depicting light as a wave is not actually a wave, all the time. By which what I mean, is that not only a wave, but under some situations, light can have a quantum. It can act like a particle. One experiment to prove that light is both a wave, as well as a particle, is the photoelectric effect. Well, according to the wave theory of light, light ejects electrons from a metal surface, when it hits the surface as a radiant wave, giving out its energy to the electrons. According to the theory, if we increase the intensity of the light ray, we increase the strength of the waves, hitting the surface, and thus, the number of electrons ejected, are increased. Also does the electrons get a higher pace, and achieve a higher kinetic energy. The frequency of the light ray, according to the theory, makes no difference. However, wave theory of light fails to be proved correct, so, we need some other theory to explain the phenomena. We came up with the particle theory, which says that electrons get ejected from metals, when individual particles, or quantums of light, strike the metal surface, and electrons interact with them one by one, individually. Particles transfer their energy to the electrons, which is used to overcome the positive charge, pulling it towards the nucleus. If the particle's energy meets the requirement of the electron, the surplus energy is given out as kinetic energy to the electron, and the particle destroys in the process. Whereas, if it does not meet the needs, it gets rejected. The minimum energy, required by the electron to pop out, is called its work function, denoted by W0. The work function of a metal depends on its ionization. So, according to the particle theory of light, energy is equal to the work function plus the kinetic energy. Another equation, proposed by Max Planck, the founder of quantum mechanics, is that energy is equal to Planck's constant times the frequency of light ray. Combining the two equations, we get to know that Planck's constant times the frequency of light ray is equal to the work function plus kinetic energy of light ray. Thus, Planck's constant, as well as the work function, being a constant, if we increase the frequency of light ray, the maximum kinetic energy achieved by the electron should increase. Also, according to the theory, increase in the intensity of the light increases the number of particles of light, which in turn increases the number of electrons ejected. And this truly happens. Experiments showed the same results. So, particle theory of light proves out to be correct. However, it does not explain all the phenomenons. The ones it does not, can be explained by the wave theory. But it too does not explain all of it. So which one should we choose? Albert Einstein provided us with the answer for which he got his Nobel Prize. That was that he introduced us to photon, the particle of light, which was a part of a wave. This explained everything and created the dual nature of light. But, not only does the waves act like a particle, but particles too can behave like waves. One such experiment to prove so is the double slit experiment. Well, if we randomly shoot out marbles through two slits at a screen, and record the data of places where the marbles hit the screen, we without any doubt will see maximum hits directly behind the slits. These were classical physics results. However, according to quantum physics, the results are different. An experiment has been performed with an electron, a subatomic particle, but with smaller slits and distances. This time, there was a stripped pattern, with a region of more hits, then one with less, then with more, then with less, and so on and so forth. Only one known phenomenon creates the same pattern. Waves. It be water, sound, or light. One wave splits into two, and then both of them when meet, interact, and create this pattern. Well, this leads to the discovery of wave of probability and quantum entanglement. But we won't be talking about them. Right now, what we care about is that the experiment proves that particles can behave like waves. This is called the wave-particle duality. Waves can behave like particles, or particles can behave like waves. And the fact that the experiment with marbles does not show the striped pattern is because the wave behavior it depicts is of a higher wavelength and higher energy. Thus, the experiment also proves that quantum physics is way different than classical physics due to the difference in the length and energy measures. So, in general, quantum mechanics tells us that everything is quantized. It tells us about the wave-particle duality. Also, we get to know that it is different from the classical physics. Hope you liked the video.